What do you see when you think of nothing? You might imagine a vacuum, a region of a universe drained of all matter and radiation. But go further. Try to think of true nothing, an absolute nothing. This nothing is not just empty, but devoid of space and time themselves. Given our everyday experiences, this is almost impossible to imagine, but humanity has always struggled with the concept of nothing. Science and cosmology tell us something even more shocking. Our universe has not existed for eternity. About 14 billion years ago, it had a beginning, a fiery birth in a maelstrom of particles and energy. And the most unsettling question of all, what came before? Scientists offer tantalizing possibilities. Maybe our universe was begotten from a previous existence, part of an endless cycle, or formed in the violent collision between two other universes. But the most radical answer is that our universe was born from nothing. And if that is the case, how does one get something from nothing? Stay until the end, because quantum physics has an answer that defies all your logic. A question: is one electron as real as zero or two electrons? When electric or magnetic fields are at zero, are the fields still there? These might seem like strange questions, but by the early 20th century, our notion of physical reality had become somewhat fuzzy. Newton's rigid clockwork universe had been replaced. Einstein had turned space and time on their heads with his theory of relativity. And experiments showed that the world of the very small, the world of atoms and electrons, was governed by a totally new set of laws, quantum mechanics. In the subatomic universe, physicists spoke not of certainties but of probabilities. And here's the paradox. Our macroscopic, large-scale world is one ruled by certainties, by things by reason and logic. Nothing is nothing. Something is something. When you put your cup of coffee on the table, it stays there every time. Yet, the distant world of the very small, the strange quantum world in which something can be born out of nothing, and matter can pass through matter, has more an effect on us and the entire universe than we might think. We are going on a journey across time and space, from a universe's first moments to its far-flung future. We are going to unpack the meaning of quantum mechanics and explore its impact on the cosmos around us, leading us to the biggest question of all. Just where did the universe come from? The key to this mystery lies in an epiphany that happened on a small, isolated island in the North Sea. Werner Heisenberg, a young physicist, had been trying to understand the rapidly changing landscape of early 20th century physics. He understood that in an atom, electrons orbit a nucleus. But if these orbits were like planets orbiting the sun, the atom would collapse in a fraction of a second. His attempts to describe electron motion had failed. Fleeing a nasty case of hay fever, he sought sanctuary on the small island of Heligoland. And there, in the cool, fresh, salty air, he was hit by a revelation that totally changed our understanding of reality. It had all begun in 1900 with Max Planck's desperate attempts to explain how hot objects glow. To agree with experiments, Planck added a new, unexpected ingredient. He restricted the energy to distinct individual chunks. By quantizing these jiggles, quantum mechanics was born. By 1925, Erwin Schrödinger wrote down his wave equation. Objects like electrons were no longer in a particular place. Instead, they were fuzzy and spread out, described by something known as a wave function. Heisenberg realized that we can never actually observe an electron in its orbit. What we see are the frequencies of light emitted as electrons jump from one orbit to another. So, why bother trying to calculate the details of the orbit? He decided what we should calculate is what we can actually observe. A new mathematical way of explaining the world of the very small, but what a bizarre world he had found. The quantum world was not one of precision, but of probabilities. Staring at his equations, Heisenberg realized a vagueness in a particle's position and speed were in fact related. The more accurately we can discern the position, the less certain we are of the speed. And if we try to accurately determine speed, the position is fuzzier. This is Heisenberg's uncertainty principle. Imagine you put an electron in a tiny box. In the classical world, you could cool the electron down to absolute zero, and it would sit at rest. But the Heisenberg principle strictly forbids this. No matter what we do, there will always be some residual jiggling. And that's not all. Like position and velocity, energy and time are not precise things in quantum physics. The energy of things can fluctuate over time with small quantities appearing and disappearing on tiny timescales, very briefly breaking the law of conservation of energy. This means that even empty space jiggles. A residual energy in the vacuum that is always there, known as the quantum vacuum. This vacuum fills the entire universe as virtual particles flicker in and out of existence. And so, in the quantum world, empty space is not really empty. Nothing, it turns out, is something. The uncertainty principle is a fundamental law of the universe. Although it seems disconnected from our large-scale reality, it does have big implications for the cosmos, from our very existence to the birth of the universe itself. To understand quantum mechanics' role in the universe, we are going to have to think about our sun. Why does it shine? Around the mid-1800s, Lord Kelvin deduced that the sun was an immense ball of hot gas. With the physics of the day, he calculated that the sun's lifespan could not be much more than a few tens of millions of years. This dismayed geologists and biologists, as it allowed too little time for evolution. Lord Kelvin did not know about the physics of the nucleus. By the 20th century, physicists realized that the atomic nucleus, thousands of times smaller than the atom, require an immense force to counter repulsion of the positively charged protons crammed into the tiny volume. They unimaginatively called this the strong force. If this force could be tapped, energy would be unleashed. In 1920, Cambridge astronomer Arthur Eddington put two and two together. The power of stars lay within the nuclei of atoms. Starlight is generated by nuclear fusion, when lighter elements like hydrogen are bound together into heavier elements. But just how did this work? Protons, being positive, repel through electromagnetism. For fusion to work, nuclei must be thrown together hard enough to overcome this repulsion and for the strong force to latch them together. The problem is, a star's core is about 15 million kelvins. At this temperature, the collisions between the hydrogen protons are just too gentle. The electromagnetic repulsion keeps the protons too far apart for the strong force to grip them. So, how could the sun possibly shine? And this is where the tiny quantum world comes in. The physicist George Gamow, a true polymath, realized that we cannot treat colliding nuclei like solid balls of matter. Due to Heisenberg's uncertainty principle, at the quantum level, everything is fuzzy. When two nuclei collide, they are not simply a certain distance apart. They are many distances apart instantaneously. And somewhere in this fuzzy mix, they might be close enough for the strong force to do its work. Through quantum uncertainty, the two nuclei overcome the barrier of electromagnetic repulsion, allowing them to fuse and release their nuclear energy. This tunneling through seemingly impenetrable barriers is a feature of the quantum world, and it is this that allows the sun to shine. This not only generates light, but also forges the elements essential for our existence. From carbon to iron, quantum physics, seemingly irrelevant on a macroscopic scale, is written into the operation of the universe. But the quantum world may play an even larger role. Do we only need to think about the quantum nature of the extremely tiny? Or is there a bigger question? Is the entire universe a quantum object? In quantum physics, we can use a single wave function to describe any number of particles. This raises a huge question. Could we write down a single wave function to account for the quantum state of the entire universe? It would be truly immense, but theoretically possible. In classical physics, if you could know the precise location and speed of every atom, you could calculate where every particle will be in the future. The future would be completely written. Quantum physics, on the other hand, is built on probabilities. Knowing the wave function today will tell me the wave function tomorrow, but not a single definite tomorrow, rather a whole host of possible tomorrows. In the 1950s, Hugh Everett III proposed a radical solution in his many worlds viewpoint. There was no single future for the universe. In this multiverse of universes, there are other versions of you. In some, you may have won the lottery. In others, you may be a rock star. Everett's ideas were too radical for the time, and he eventually left science. But the notion of a quantum universe did not leave with him. Stephen Hawking, for example, pondered whether a quantum universe could solve one of the great mysteries. whether the universe had a beginning, working with Jim Hartle. He deduced that in the early universe, the quantum nature time was indistinct. Time only really came into existence when the universe became more distinct. The singularity that dogged classical cosmology, a point of infinite density, simply didn't occur because there was no real time when it could have. But the role of quantum physics in the beginning of a universe goes even deeper. We must travel back in time to the first trillionth of a second of existence. In the 1970s, physicist Alan Guth had a problem. He needed to hide magnetic monopoles. Theory suggested that in the initial superhot, superdense state, the laws of physics should be simpler. With a single superforce that fractured, within this superforce, there should be monopoles, but they appear to be undetectable in the observable universe. Guth hit upon an intriguing solution. What if the universe underwent a rapid burst of expansion when it was very young? This inflation would dilute the number of monopoles. Looking at his equations, Guth saw that this inflation could also explain why the universe appears so smooth on large scales. But inflation did much more. This inflation blew up a tiny chunk of space to the size of the universe around us. And as this tiny chunk was so small, it would have been quite smooth and homogeneous. But even this smooth chunk would still have hosted the quantum vacuum within it. Heisenberg's uncertainty would still have brought energy and matter in and out of existence. When the universe inflated, these minuscule quantum fluctuations would have been frozen into space. As inflation ended, its energy was dumped back into the universe as matter and radiation, and the frozen quantum fluctuations resulted in slightly more matter in one place than another. These differences were tiny, less than 1 part in a billion, but as the fires of the cosmic birth dimmed, gravity started to play its part. Clumps of matter and gas began to pool until a few 100 million years after the Big Bang. They were dense enough to form the first stars. Quantum fluctuations frozen into the universe and inflation became the seeds of galaxies today. We still see them written into the ancient light of the cosmic microwave background. But there is one step further back to go. Could we use quantum mechanics to confront the ultimate question of where our universe actually came from? In 1973, young physicist Edward Tryon heard himself speaking during a lecture. Maybe the universe is a vacuum fluctuation. Tryon was trying to unpack the bizarre implications of the quantum vacuum, how the energy in a vacuum can fluctuate, very briefly breaking energy conservation. He wondered what the total energy content of the universe was, the sum of all the mass, motion, and the negative potential of gravity. He thought, what if all this energy balanced out and the total was zero? Staring at the uncertainty principle, Tryon realized a fluctuation of zero energy could last forever. Perhaps the entire universe was just a quantum fluctuation. Of course, this raises the immediate question, where did this fluctuation occur? Which would just leave us back at the start. Where did the quantum fields come from? We now know that in our quantum universe, it is possible to draw something from nothing. But what could happen inside a true nothing, outside of time and space? That still remains a question beyond the borders of science. What we do know is that within the first tiny moments of existence, quantum mechanics inevitably played a role. But what about the very end of time? In the vast distance of the future, stars will die. Even the feeblest red dwarfs, which last for tens of trillions of years, will eventually be extinguished, leaving only a dark husk slowly losing its heat. Gravity will continue to squeeze these dead stars, but the uncertainty principle has one last card: quantum degeneracy pressure, which halts the collapse. The dead stars will sit there in the darkness for eternity, but not quite. On immense time scales, the question arises about the stability of matter. Scientists hint that protons may not be eternal. On time scales of 10 carat 36 dollar years, undetected forces could cause protons to disintegrate, and so the matter in dead stars would simply melt into darkness. Once they are gone, only black holes remain, distortions in time and space. They might seem impervious, but quantum physics ensures their time is also limited. The culprit, again, is the uncertainty principle. It was Stephen Hawking who first realized that the quantum vacuum spelled doom for black holes. Near a black hole, the past and future are firmly separated. This disrupts the state of the quantum waves in the vacuum, and virtual particles become real ones, tapping into the black hole's energy. As the particles, the Hawking radiation, flow away, the black hole steadily evaporates. It is here we seem to reach the end of our cosmic journey. Or is there more to tell? Since 1958, physics has been abuzz about a theory of everything that would unite quantum physics with Einstein's gravity under a single mathematical umbrella. GPS is a testament to relativity, and the LHC is a testament to quantum mechanics, but their languages are simply incompatible. The century-old search continues, and we have an explosion of ideas. Is the world ultimately made of strings? Is loop quantum gravity correct? But let's pretend, if we had this theory of everything, where would we look first? Into the black hole. With general relativity alone, all the mass in a black hole is squeezed into a single point of infinite density, and infinities really have no place in physical theories. The hope is that within the theory of everything, the singularity never occurs, prevented by quantum physics. In the next episode, we will explore how the theory of everything may unlock the final secrets of the cosmos, and what the black hole singularity might reveal about the deepest structure of reality. Do you think the theory of everything will be discovered in our lifetime? Drop your prediction in the comments below.